Hey there, it's Shannon Math Chick Myers. I hope you're having a wonderful day. Today what we're checking out are space coordinates and vectors in space. So when we're all done, you should be able to understand the 3D rectangular coordinate system, analyze vectors in space, and use 3D vectors to solve real-life problems. So let's warm it on up. Go ahead and pause the movie and find some vector v that has a magnitude of 4 in the same direction as a vector u, which is equal to negative 1, 1. On your mark, get set, go! I know you can do it. Okay, let's see how you did. We know a couple things, right? We know that u is equal to this vector, negative 1, 1. And we know that if we divide u by its magnitude, then we will have the unit vector that's going in the same direction as u. Good so far? Awesome. So let's do it. We know that u is negative 1, 1 in component form. And then, so the magnitude of u is going to be the square root of negative 1 squared plus 1 squared. That's going to give us, beautiful, 1 plus 1 is 2. So what we're going to end up with is the vector negative 1 over root 2, comma 1 over root 2. Cool so far? Awesome. So now v needs to have a magnitude of 4 and be going in the same direction. We've created this vector that's going in the same direction with the magnitude of 1. So v is merely going to be equal to 4 times this vector that we found, which was u over the magnitude of u. And that's going to be 4 times, negative 1 over root 2, comma, 1 over root 2. Now we might want to, if you rationalize 1 over root 2, we'll clean it up a little, you'll get 4, and then negative root 2 over 2, and root 2 over 2, 4 being multiplying to that vector. And at the end of the day, v will be, beautiful, negative 2 root 2, comma, positive 2 root 2. Cool so far? Awesome. All right. So now that you're all warmed up, let's check out the three-dimensional coordinate system. All right. So here, this is what we have going on, and you've basically got your x, y, and z, and so you end up with these different planes, planar regions. So if you're looking at, say, the xz plane, you're going to have something like, let's see how well I can make it here. You'll have something like this. You want to be going parallel to z. Something along these lines. Something like this, you know, it's not perfect, but you basically, this here would be your XZ plane. And then your XY plane, in this case, would be more like this. You now be going more parallel to your Y plane, and then parallel to your X axis there. Sorry, I'm making this one kind of huge. So you'd have something like this. And this one here is your XY plane. And then the YZ plane is going to look more like this one. So now you've got your YZ. So it will be, we'd be going parallel to your Z and your Y. So you'd be getting something that looks a little bit like this. Cool so far? All right. So basically what ends up happening is, taken as pairs, the axes determine 3 coordinate planes: XY plane, which was the middle, XZ, which was the left, and XYZ, which was the right one. Okay, so YZ, XY, and then XZ was over there. So these planes separate 3 space into 8 octants. Okay. In this 3D system, a point P in space is determined by an ordered triple, and that is denoted XYZ. So X is the directed distance from the YZ plane to some point P. Y is the directed distance from the XZ plane to some point P. And Z is the directed distance from the XY plane to some point P. So a 3D coordinate system can either have a left-handed or right-handed orientation. The right-handed system has the right hand pointing along the x-axis. Our text uses the right-handed system. Okay? So now let's check it out. For our first example, I already put in the 3D coordinate system for you. And what we want to do is plot the following points, A, B, and C. So A is 1, 0, 4. So I'm going to take a look. This one is going to be on what? Which plane? Because something zeroes out. Beautiful. That it's going to be the XZ plane. So if we let each one of these equal to half, each tick mark, what's it going to end up being? 1, 2, 3, 4. Okay, hopefully that'll work. So for A, we'll use, why don't we go ahead and use purple for A. So 1, and then 0 on the y-axis, and then 4, we want to go 4 up, but remember it needs to be parallel to the x. So you're making this kind of trace up. So it'll be somewhere, at the end of the day, it'll be somewhere around here. Need to make it that huge. And so let me kind of erase some of the other stuff. Okay, so this one is our point A, which we said was 1, 0, 4. And then our point B, we'll do in blue, that's negative 2, 3, 1. So this one will be a little harder because it's not just on a single plane. So here, if we do take a look at what negative, like just plotting negative 2, 3, so 2 back for the x's, and then 3 over here. So actually that would be, right here is 2 back, and then It'll look something like this. And now what we have to do is we need to go parallel to the y and the z axis, and the z is at 1. And so here's our 1 right here for z, right? So we need to go up to about here. And we should have it, because it's gonna be going up about that 1, so it'll be about there. That's our B. And then our C, whoops, sorry. Our C is -2, -1, 4. So we'll do that in pink. So -2 is back here. And then -1 about here. And then now we need to go down 4. So it's going to be about, remember, you've got to still look at the angle, so it's not going to look like it's right at that -4, because it's going to be parallel to that plane that we had reached. So these are the points in the 3D. Okay. So, and that was C. Something like that. So now the main thing is to kind of make a rectangle with your first two, and then figure out where to go up from there. So the distance between 2 points in space is going to be basically just an extension. You know the distance formula for the plane. So it's going to start out the same. But then you also have your z2 minus z1 squared. Cool so far? All right. So here on our first example, or second example, find the standard equation of the sphere that has the points 0, 1, 3, -2, and -2.2 as endpoints of a diameter. Okay, so for the center, we need to do a few things, right? The center of the sphere, let's just call it x0, y0, z0. And the general equation for a sphere looks like this. So it's going to be r squared is equal to x minus x0, the quantity squared, plus y minus y0, the quantity squared, plus z minus z0, the quantity squared. Cool so far? Now, what do we need to find? We should probably find the midpoint, right? The center. So for each of these, if we find the midpoint, because we were given each of these, we were given that each of these endpoints, it was an endpoint of a diameter, so it's somewhere on the sphere. So if you cut it in half, won't you have the radius, right? So there are actually multiple midpoints. So our x0 would just be 0 plus -2 divided by 2, which is equal to -1. And I'm getting that because, remember, a midpoint in the plane is just going to be your sum of your x values divided by 2, sum of y values divided by 2. So our y0 then will be equal to what? Beautiful. 1 plus 4 over 2, which is 5/2. And how about our z0? Let's see, 3 plus 2 divided by 2, which gives us another 5/2. So what have we found? We found that the center of the sphere is -1, 5/2, and 5/2. Now we only need to use the center and whichever one of the ordered triples that we were given to find r. So let's go ahead and use the center, and this first one has a 0 in it, so we'll use those two. So now we're basically r is the distance between those two ordered triples. So what we're going to find is that r will be the square root of (0 minus -1, the quantity squared. I'm getting those from the x coordinate from the circle point on the diameter that we're using and the x coordinate at the center, plus 1 minus 5/2 squared plus 3 minus 5/2 squared. Cool so far? So what's that going to be? R will end up being the square root of 1, because 1 squared is 1. And then we'll have plus, well, 2/2 minus 5/2 is -3/2. And when you square that, you'll get 9/4. And similarly on this one, what will we get? We'll get 6/2 minus 5/2, so we'll get 1/2. We square that, we get 1/4. So then, r will equal to the square root of, for this one, 10/4 plus 4/4 is 14/4, which is, sorry, I'm left-handed, 7/2 under a square root. So now we just need to write our equation. We'll come back to our general form. So here, this was just our general info that we needed. This was stuff we needed to find the center, right? Of the sphere. This one, find r. And now that we've put it all together, we'll write our equation, okay? So the final answer will be r squared, so 7/2 is equal to, and now we'll let x, y, and z vary, and we'll have, so remember our general equation, x minus x0. So my x was 0, or I'm sorry, my x0, I'm using the center of the sphere. So we'd have x minus -1 squared plus 5y, minus 5 halves squared plus z minus 5 halves squared. Cool so far? And then of course we can write that as 7 halves equals x minus 1 squared plus y minus 5 halves squared plus z minus, z minus 5 halves squared. And we're done. Cool so far? All right. So now we've got some definitions of vector addition and scalar multiplication. And so if we let u equal to, the vector u equal to u1, u2, and u3, v, the vector v, equal to v1, v2, and v3, they're vectors in space. So that means that ui and vi are real numbers, and c is a scalar. So equality of vectors. U equals v if and only if, well, what do you think? u1 would have to be equal to v1. The components got to equal to each other. u2 has to equal to v2, and u3 has to equal to v3. Component form. If v is represented by the directed line segment from p, which is p1, p2, p3, to q, q1, q2, q3, then how did we do that before? Well, v, we want it as v1, v2, v3, but what is that in reality? It's going to be equal to q1 minus p1, remember this from last time, comma, q2 minus p2, comma, q3 minus p3. And we're using the other kind of brackets. Okay. Okay? So just an extension of what's happening in the plane. Now, length, the length of vector v is just going to be the square root of v1 squared plus v2 squared plus v3 squared. So you just sum up the square of each of the components and square root it. All right. So the unit vector in the direction of v. Well, remember, you just divide that vector v by its magnitude. So what happens? You're going to get 1 over the magnitude of v times the vector with the components v1, v2, and v3. And of course, v can't be equal to the 0 vector because then you'll have an indeterminate form, and that's no good. All right, vector addition, v plus u is going to be v1 plus u1, v2 plus u2, and then v3 plus u3. And scalar multiplication, you do scalar times v, and you're going to get cv1, cv2, comma, cv3. All right, so now find the component form of the vector v that has initial point -1, 6, 4 and terminal point 0, -5, 3. And then let's also find a unit vector in the direction of v. So, okay, go ahead and pause the movie if you want and work it on out. I'll give you a minute and then I'll come back. On your mark, get set, go! You can do this! Woo! Okay, let's see how you did. So to find the component form of v, what do we need to do? Remember, we need to subtract the initial point coordinates from the terminal point coordinates that correspond. So what's going to happen? we'll have 0 minus negative 1, comma, negative 5 minus 6, and then 3 minus 4. And so that's going to give us that V is equal to 1, negative 11, negative 1. Good so far? All right. So now what? Now what are we supposed to do? We're supposed to find a unit vector in the direction of V. So we finished with our first part. So now, what's the magnitude of V going to be? Good. It's just going to be the square root of V1 squared plus V2 squared plus V3 squared. Well, what's that going to equal to? Good. That's going to be equal to the square root of 1 squared plus negative 11 squared plus negative 1 squared. So what will we get? We will get the square root of 1 plus 121 is 122 plus 1 is 123. So now a unit vector, let's call it U, in the direction of V is going to be U equals V over the magnitude of V. So we will have U is equal to 1, negative 11, negative 1, that vector, over the square root of 123. And so that if we bring that in, U will be equal to the vector 1 over root 123, negative 11 over root 123, and negative 1 over root 123. Cool, cool? So we're all done. Took a few steps, but we did it. Okay, parallel vectors. So parallel vectors, two non-zero vectors u and v, are parallel if there's some scalar c such that u is equal to c times v. Okay? So it's just scaled, and that means they're going to be parallel. So here we go, example 4. Vector z has initial point 5, 4, 1 and terminal point negative 2, negative 4, 4. Determine which of the vectors is parallel to z. Well, let's see, what is z? I mean, z is going to end up being equal to, let's see, negative 2 minus 5, comma, negative 4 minus 4, and then 4 minus 1, which gives us negative 7, negative 8, and 3. So that's the component form of z. So now 7, 6, 2, what do you think? Is there some scalar that will work to get set, a 7, 6, 2 out of, multiplied to some c to get negative 7, negative 8, and 3. So, what do you think? Is there something you can find? Well, it's really kind of a system, right? It means 7 times c would have to equal to negative 7. 6 times c would have to equal to negative 8. And then 2 times c would have to equal to 3. So the first one, I would get c is negative 1, right? But the second one, I had a different answer for C. It would be negative 8/6, which is negative 4/3. And this one, you would get C would have to be 3/2. So we would say no for this first one. Good so far? But the second one, okay, 14C would have to be negative 7. 16C would have to be negative 8. And 3C would have to be negative, oops, sorry. Not 3, we would have negative 6. Negative 6C would have to be equal to 3. So for the first one, we would get C is equal to negative 7/14, which is negative 1/2. For the second one, C would be negative 8/16. Ooh, it's looking good, which is negative 1/2. And for the third one, C would be negative 3/6, which is negative 1/2. So, yes. Cool, cool? Okay, so next up, example 5. We want to find the component form of the unit vector v in the direction of the diagonal of the cube shown in the figure. So, what the heck do we have going on here? The magnitude of v we know is 1, okay? And so that purple vector is v, and we know that the length of it is 1. Now this is a cube, so every single edge is the same length. Cool so far? So what if we were to find like this diagonal, right? So here, basically, if we took a look at this diagonal, right? This here is gonna form, sorry, that's kind of thick. I don't want to do it so thick. Now, right here, this is going to form a right angle. That looks terrible, sorry. Do a different color. This forms a right angle right here, okay? So if we could figure out this triangle, so I'll highlight it. If we could figure out what this triangle was, then we could figure out what V would have to be, okay? So let's do it. If we call each edge E, right? This diagonal right here, so we'll do it in blue now. This diagonal, the diagonal of, basically, it might be easier to see if we brought it up here. So this is going to be the same diagonal measure. So if you look at the top square here, do you see that you'd have an edge and an edge, right? And you can find that diagonal in terms of E. So our diagonal squared is going to equal to E squared plus E squared. And so diagonal squared is 2 E squareds. And so D is a length. So we're going to have E root 2. Good so far? So we found that this diagonal is E times the square root of 2. Now, we're going to utilize that fact to solve that yellow circle, right? That has that right angle. And so here, remember that down here, this is also D. Right there. And so we are looking at finding, I should have used highlighter, but we're looking at finding, whoa, way too fat. So we're looking at finding this triangle, and we know that right here is an edge, is E, and we know that our vector, which you can't really see anymore, it was in purple, and it went from here to here. This right here was our vector V, okay? And the magnitude is vector V is 1, so just using our right triangle trig, that magnitude is the hypotenuse in this case. So we would have d squared plus e squared is equal to the magnitude of V. Well, we know that d squared is what? Beautiful. 2e squared, right? So we'll have 2e squared plus e squared, and we know that the magnitude of V is 1. So 3e squared is 1. So e squared will be 1/3, and e will be 1 over root 3. Again, it's a length, and so it is a length, and so therefore it is going to be positive. So what have we found? We found that V is equal to 1 over root 3, 1 over root 3, 1 over root 3, and you can also write that as 1 over root 3 I plus 1 over root 3 J plus 1 over root 3 K, if you want to. Cool, cool? All right, so anyway, I think that's it for today. Woohoo! So go ahead and pour yourself a glass of wine, have a margarita, and I hope you have a wonderful morning, afternoon, or evening whenever you're listening to this. And if you like what I'm doing, hey, subscribe and tell your friends. Thank you. Bye.